Well, thanks so much for the invitation. So it's going to be fast, but please come talk to me after my talk if you want to know more. So today I'm going to talk about the design of protein nanomachines and how we can use generative AI now to generate them at scale and with a pace that was not possible before. So as many of you know, I'm sure, protein folding has been around for a while, and so we can use computers to kind of like manipulate proteins. And so we can go from a sequence to a structure. And more recently now, we can specify a structure, so atomic coordinates essentially, and then find, using computational methods, we can find a sequence that would encode for that shape. So it's not really printing, as a lot of you have been discussing. It's more like relying on self-assembly to like pattern in 3D at the atomic scale atoms. And so now you can really specify biochemical blueprints. So you can place atoms in 3D again. You can specify secondary, tertiary structures. You can use symmetry and like macromolecular assemblies. And then using either physics-based methods to like minimize the energy of the structure, or more recently, machine learning-based methods, you can end up finding structures that correspond to your design specifications. And so more traditionally, we were using more physics-based methods, and so that worked pretty well. But as you can see, you could sometimes find, kind of like when you explore the energy landscape, the landscape of structures, you could find off-target, assemblies. And so machine learning really changed that because now it's much more efficient the way we sample the space. And so it's like it works much better. And so I gave a talk a year ago, and so I can say that since then we've really like increased the scale of just like computational methods, and so AI really changed a lot of all that. So we published recently like protein impedance that allows you to find sequences that encode specific backbone structures very efficiently. We can do hallucinations, so we can essentially like sample these like deep learning models to try to find solutions to specific design questions. We can use reinforcement learning to specify specific like backbone constraints and try to find best solutions for those. And then more recently, we have these diffusion models now that allow you to design at the atomic scale, both the backbone and the sequence at the same time. And so all of those are really virtualizing the whole space, and it's going really fast. And so even for us, it's hard to keep track sometimes. So then in the end, you have a sequence that you can like put into a synthetic gene and a bacteria, and you can have an organism actually create your protein machine. And so a few years ago when I started, I wanted to kind of like explore the space of what we could design de novo with proteins. And so looking at nature is pretty amazing. All these like very intricate protein machines that have evolved over the years. And then I thought maybe we could start by building simple machines like what we do at the micro scale, and then start putting them together to eventually make things that start looking like very complex little protein machines. So a project that we published now a year ago. So we started working on these machines by trying to take a little proof of concept of a little machine, and one such machine was a rotary machine. So it's a mechanical system made of like multiple components that can self-assemble, and they have this rotational degree of freedom, right? So it's a machine that's allowed to rotate its components relative to each other. And so we came up with like a blueprint, designed protein components, designed them so that they can self-assemble again, and then they are locked together in solution, and they can only move according to these mechanical constraints. So those are not powered yet, and I'm going to talk about powering now. And so just like an example of like a pretty cool design. So this one has like 24 individual components that self-assemble into solution, and they come together into this highly symmetric particle that has these two rotational constraints. And so we could find, when we put these molecules in the microscope, we can see that actually can rotate according to specifications. So now we're really trying to explore the space of like what can be designed with these methods. And I don't have time to go into much detail, but now we can make things that look like more complex, that have like many movable parts. We can make things that can be activated by light or different chemical fuels. We can embed these machines in membranes, so we can harvest chemical gradients to power rotation, for example. And then we're starting to think about designing motors that have, that are more efficient. We can make things that can move along one-dimensional tracks. And we can also, interestingly, like study the physics of molecular motors by using these computational methods, and that can also inform back our design process. So I'm very happy to talk about all these different approaches. I don't think I have time to go into much detail. But with that, yeah, I want to thank a lot of brilliant people at the IPD, and especially David Baker, and all my collaborators, and I'm happy to answer questions.
Wonderful. Thanks so much. So we have about a minute or something for general questions, and then we get on the collaborative doc, and I want you and perhaps all of you guys to perhaps give us a few ideas of how Alexis' presentation could fit into one of the architectures. Any questions, comments before that?
Can you comment on what is the yield of the assembled motors of these multi-component systems?
Right, that's a very good question, and unfortunately it's not something that we've looked into. What we know is that the bacteria is pretty efficient at assembling it. It's very hard to evaluate because everything that's not assembled properly is going to be unfolded, and so we don't actually purify it. So that's a very interesting question and something we should look into. We know also we can assemble it in vitro, and that works pretty well. But again, like the yields are kind of difficult to evaluate.
Thank you. So my question is, once you have these machines assembled, do you have a way of going to the next level of hierarchical assembly to put them into bigger combinations of machines?
Yeah. Do we have a way to do that?
Yeah.
Yeah, absolutely. So we can really design, we call it hierarchical design. So we can design one component and then another and then another one. And so we can really like scale up hierarchically the design process.
So it's super impressive. What's missing? Is it just time, or are there still like fundamental challenges?
Right. So it's a very good question. So like now the methods have advanced enormously. And one of the big limitations for this field is the big bottleneck is like biophysical measurements. So it's easy now to design and get something that has the right structure. But before we can assay it as a single molecule level, that takes a long time, right? So it's like a PhD worth of single molecule biophysics to know how the machine is going to perform at the nanoscale. So that's definitely a limitation, and so I'm very happy to talk to all of you about that if you have.
Thank you. Stay up with me for a second, because now we're going to go onto our collaborative notes doc here, where people have already started taking notes on your presentation. So if you open it right at the hour where we are, 11:10, people have already started collaborative taking notes on your presentation. And the discussion prompt also for you, and perhaps you can fill it in afterwards if you don't mind. How does the presented approach fit into one of the architectures? Like if you had to pick one of them, where would you be like, okay?
Right. I think that's an interesting question. So I wanted to comment on the documents about that because I think this approach relies on, again, self-assembly, right? So there's no printing. It's all like you actually like program the components in the computer to self-assemble in solution at the atomic scale. So in a sense, you don't have to rely on these like very complicated, kind of like atomic scale finger kind of things, but you really rely on the folding process. And so that's what nature decided to do, and I think that's for a reason. It's because it's extremely efficient. So the ribosome is made of like hundreds of components, and they all, fold together in solutions. And I think this is what we should, start addressing because we have the tools now. So AI allows us to do that, and I think it's much more powerful than just printing.
Sorry, can I just get a clarification? So your vision right now is that you're assembling these things within a cell. The cell is actually producing the proteins, and you're just letting them go together. Is that?
Yeah. So that's a route for synthesis. We can also do it chemically. So you can do like like solid state peptide synthesis. You can also do like in vitro expression. So there's different routes. And so I think that like the full like synthetic chemistry for like peptides might be a very interesting route for like designing very complex things, right? Because it doesn't rely on biology.
Okay, wonderful. Thank you so much, Alexis.